Good evening. My topic is the types of nuclear reactions, that is alpha decay, beta decay, and inverse beta decay. So, now first let's see alpha decay. So, why does alpha decay occur first of all? If we say the nuclear forces, that is attractive forces between the nucleons, it is a short range force. So, the total binding energy of the nucleons is approximately directly proportional to the number of nucleons, which is the mass number of the atom. So, but the repulsive electrical force between the protons, they are of unlimited range. That is why the total disruptive energy, that is the energy required to break the nucleus, is approximately directly proportional to Z square, that is atomic number square of the atom. Now, if we have a big nuclei which contains 210 or more nucleons, then the short range nuclear force that hold them together, that is attractive force, that cannot counterbalance the mutual repulsion of their protons. So that is why alpha decay occurs, which is to increase the stability of the nucleus and reduce the size, which is already very big. So during this alpha decay, what happens is an atom, if it is having an atomic number Z, then that is the parent nucleus. It gives birth to a daughter nucleus which is having an atomic number Z minus 2. And an alpha particle is emitted, which is a collection of 4 particles, or essentially we can tell it as a helium nucleus. So this reaction which is given here, you can see that is the actual reaction that takes place in an alpha decay. So if we take an example of this radius nucleus, when it undergoes alpha decay, it breaks up into a helium nucleus first, that is He2 plus, and a daughter nucleus that is that has an atomic number Z minus 2. Z is the atomic number of radius, and the daughter nucleus is formed as radon, which is having an atomic number 86, that is 2 less than the atomic number of radius. Next, if we see this alpha decay, there is a picture of alpha decay. You can see that this element, it divides into 2. That is, the first one is the daughter nucleus, which has Z minus 2. See, it is given that it is missing something. It is missing this Z minus 2. And the other one is the helium nucleus, which is having 4 particles as it is shown here. That is helium 2 plus. Next, let's go for beta decay. If you see in beta decay, what happens in beta decay actually is the nucleus, it alters its composition to become more stable. So in beta decay, what happens? One of the neutrons that is inside the nucleus, it suddenly changes into a proton, which therefore leads to an increase in the atomic number, that is Z plus 1, if Z is the atomic number of the parent nucleus. So this reaction changes the number of protons in the nucleus to be. So this is the reaction. These two reactions are the actual reactions that take place in beta decay. That is, a neutron gets it is converted into a proton. So there is an increase in the atomic number of the atom, so this, in addition to changing its atomic number, the nucleus creates and releases an electron from the atom. In the reaction, you can see that it releases an electron also. So why it is releases? It is to counterbalance the positive charge it gained by transforming the neutron to a proton. So to counterbalance that proton only, this electron is emitted. Plus another additional particle is emitted, which is known as the antineutrino, which is having a very small mass, or we can neglect the mass of antineutrino. So the next reaction, we can see that the parent nucleus is there, that is X, Z atomic number and A mass number, which gives birth to a daughter nucleus that has an atomic number Z plus 1 and an electron and an antineutrino. You can see, for example, potassium, which is a parent nucleus. The daughter nucleus just formed as calcium, which is having 20 atomic number, where potassium is having 19. So it, plus electron plus antineutrino is formed. So this is the potassium chloride, which is sold as a salt substitute in grocery stores. So the product, which contains traces amounts of potassium, which tends to undergo beta decay into calcium, the above reaction denotes this. This is the above reaction. Next, we will go for positron emission. Positron is another type of particle. It is also type of beta decay only. It decreases the atomic number because a proton, it gets converted to a neutron. So the atomic number of the nucleus when a proton becomes a neutron is decreased, because a proton is becoming a neutron. So now due to this charge conversation, this type of beta decay involves the release of a charged particle called positron, which is E plus. Electron, if you say, it is E minus, positron is E plus. So it looks and acts like an electron only, but it has a positive charge. That's all. And in addition to it, here a neutrino is also released. That is, another particle is released. So in that beta decay, there antineutrino is released. Here in positron emission, neutrino is released. So in this, if we can divide this beta decay into two ways, two types, that is when the beta decay creates a positron, that is in this positron emission, this is called as beta plus decay. And when it creates an electron, it is called as beta minus decay. So this one is known as beta minus decay, and this one is known as beta plus decay. This is called positron emission. These are the two types of beta decay. So next, let us come to medical application of beta decay. That is, the particles and because this particles interactions with other tissues are easily identifiable. The particles is released during the beta decay, that is this positrons, neutrino, antineutrino, their interaction with other tissues are easily identifiable. So some medical imaging techniques involve purposefully injecting a patient with an element that beta decays into positrons and then monitoring where the positrons are emitted. So this is how it is applied in medical field. That is, a patient, he is injected with an element that will beta decay into positron. That is, it will do this beta plus decay. So that will undergo beta plus decay. A patient is given an element, he is injected with an element that will undergo beta plus decay. So this positron, after it undergoes beta plus decay, positron will be emitted. Now after this positron's interaction with other tissues is easily identifiable. So we can monitor where the positrons is emitted, and that can be applied in medically. Next, this is the beta decay picture. That is, you can see that the parent nucleus, it forms a daughter nucleus which is having an atom, which is having Z plus 1 atomic number, and the other one is an electron. So here it is showing as a changed man because the daughter nucleus is another element is formed, so it is totally changed. Next, let's go for inverse beta decay. So this inverse beta decay, here what happens is, if you see, the absorption of an antineutrino is equivalent to the emission of a neutrino and vice versa. So the absorption of an antineutrino, you can see, it is given as this reaction. This is the antineutrino plus proton, which gives an electron, a positron plus a neutron. So this is the equation of absorption of an antineutrino. Next, if you see the emission of a neutrino, this is the before reaction, this reaction, here a neutrino is emitted. So these two reactions, if we see, these two reactions are equivalent. So these two reactions are called as inverse beta decay. So it is commonly abbreviated as IBD. Here antineutrino scattering of a proton, antineutrino scatters a proton, creating scattering of a proton, creating a positron and a neutron. So it is used in detection of electron, antineutrinos and neutrino detectors. So it is of extremely low probabilities, that is, it has a very less probability of occurring. So here in this reaction, what happens is, an electron, antineutrino, it interacts with a proton, which gives a positron and a neutron. So if we can say this IBD reaction or inverse beta decay, it can only be initiated when the antineutrino possesses at least 1.806 MeV of kinetic energy, which is called the threshold energy. This is the minimum kinetic energy which an antineutrino has to possess to undergo inverse beta decay. So this threshold energy is due to the difference of mass between the products, that is neutron and this positron, and the reactants, that is antineutrino and proton. And it is also slightly due to the relativistic mass effect on the antineutrino. Now this antineutrino energy is mostly distributed to the positron because the neutron is having bigger mass related to positron. Positron is smaller than neutron. So most of the antineutrino energy is distributed to the positron. Thank you.